You take your own time and do it.
Yes, sir. This was my topic. Basically, this is machine vision applications for assembly, inspection, and testing. This was the topic. Basically, what we did for the conference, national conference yesterday for the emerging trends in mechanical engineering. And the main abstract for this is in recent development industrial development, robotics playing a vital role in which flexible manufacturing cells and assembly stations. That means like of manufacturing automobiles or CNC machines or any other materials in mechanical industries are majorly being participated in robotic industry. So basically in this robotic vision applications, we came up for proper lighting with camera, image processing analysis, and task applications of vision system that has been taken part as part of the discussion for this seminar. And the introduction for this is will be majorly generally in general as of now what companies or like small scale industries uses machine vision which extremely uses 2D inspection of components. That will be only for 2D vision, and which they make up a 3D vision after making the 2D vision. But in this topic we can using of two or more cameras we can gain information of 3D measurements also. That is only called as robotic vision and vision system, in which in that we need robot accuracy, repeatability, and there are certain measures to be taken, and to gain an exact distance of any small material or any other product which we are processing or which we are manufacturing, we can know it with a 3D projection with two or more cameras gaining in it. And the objectives will be general 3D vision metrology, photography and camera calibration, advantages of using non-metric cameras, disadvantages of using non-metric cameras, robot accuracy. General 3D vision metrology. Basically, general 3D means it is actually doing 3D also should be happen first from 2D then 3D. Directly 3D cannot be done. But the various methods are there extracting 3D information from 2D images. In that, basically in vision metrology, we have two methods. We call it as triangulation methods, which we use stereo vision and laser scanner example, and interference techniques like holography and mirror fringe. In triangulation methods, it can offer large wind of area. Like for example, we can go for cars and we can go for building big components for the big like for example you can go for Tesla, which they are using almost triangulation methods like stereo vision and laser scanning, and even Rolls-Royce they use the laser scanning for their seat covers and seat manufacturing also. And for this there are many methods struggling with the lightning and making some of them difficult to use outside the laboratory. They need certain regulations and requirements to perform this method. In interference techniques, they usually require complicated optical arrangements, often with the coherent light source. The coherent length of the source limits the range over which reliable measurements can be taken. Problems can also occur if the displacement is in the plane. In this interference techniques, it's very important that we need certain coherent light, we need so and so, in which we have to use it with a closed room, closed surface, with less light, with more coherent light, and that comes with minute particles like minute manufacturing of small materials which can be done with 3D vision metrology. And we have for this the basic thing we can call it as photogrammetry and camera calibration. The use of two cameras to provide distance and size information is already well documented. That means in one camera we can take it for the distance, and in another it will be a size information. For example, nowadays how phones are coming with 4-3 cameras like macro lens, micro lens. So like that, if you use 2 to 3, 4 cameras in a robotic vision, that can easily come up with programs and a perfect picture of a model uh, or a material or whatever we built, whatever the company wants to build for the product, it will be done with the robot itself. If we program and if we do it, it will come with a photogrammetry on itself. It requires photographs taken using camera within unknown interior dimension metric cameras that are known as distance apart. A skilled operator then creates measurements using images. It is possible to use non-metric cameras. They have unknown interior geometry and have not been designed in minimize errors caused by lens distortion. So since, as I said here, triangular methods are now, as per what I have researched according to the vision tech methodology, 90% Tesla and the Rolls-Royce, which they use robotic, they are using triangulation methods, but they use non-metric cameras, which will which will minimize some errors. We can't say 100% errors will be done, because some manual errors it should be done, it has to be done from human itself. The advantages of using non-metric is that is general availability. You get everywhere. It's not so complicated. It's not so costly also, and flexibility in focusing range. It doesn't need so much setup for the image to take up the image of the product, or you need certain regulations like this only you have to keep the camera. No, nothing like that. Anything it might focus, and it's very flexible in focusing also. Some are motor driven, allowing for a quick succession for photographs. They are usually smaller and lighter in weight, and which is very important in robots, because we can't put a huge object or heavy object and we can't tell robot you go and get the product. So it depends, and it happens. We need small and lighter product in a robot. Is very important. They can be easily handheld and thereby oriented in any direction. They are readily available film. They are used. Doesn't seem like you take a photo camera and you get it in an image gallery. So it's like that. That is called metric cameras, where you get instant pictures or instant readily available. Maybe we can say, depending upon the resolution, it may take around 5 to 10 minutes or maximum 1 hour, depending upon the resolution of the picture available. The price considerably less than metric cameras. Comparatively to metric, non-metric is less. The disadvantages of using non-metric cameras are lenses are designed for high resolution at expense of geometric quality, as evidenced by generally large and often irregular distortion. That means the lens used in the non-metric cameras are for high resolution, which will give extensive geometric. We can say around 95% to 90 to 95% you will get an exact geometric quality in non-metric cameras. Instability of interior orientation. The absence of orientation aids such as level vitals and orientation provisions preclude the precision orientation of the camera along the desired directions. But you have to give some directions to the camera, because this is not a camera which can cover through not much wide range. But if the product is in front of the camera with the robot, yes, it will capture, but it does not take the wide range using these non-metric cameras. The absence of proper film flattering device. That means if the film is not there in the robot using the camera, the picture or the product will not be taken. It will not be done with the 3D vision. We need film to use this camera in the robot. That is the main thing. And robot accuracy, in which we can say high automated production lines due to robot failure. That statistics shows that 45% of failures are related in inaccuracy. Some robots are instinctively being created with this camera for this vision only, but some what they do is they might prepare robot for some other purpose, and they want them to do this purpose, which will reduce the accuracy of that robot, and it cannot do that work also and this work also. Like, if for example, if we say it has been prepared to draw a product with 2D, then we make arrangements for that to do 3D, then it will be an accuracy problem. So 45% of the statistics have been failed doing this. So what the major companies they suggest is, if the product has to be made for 2D, then it should be in 2D itself. We should not convert that to 3D. And the major errors which come are pose error and path error. While doing pose error, that it should not shake. If it shakes, then the film as well as the model, the outcome will be very bad. And path error in between, the product should not be even disturbed, or it should, as per the Van Brussel analysis, there are two types of errors, and path error also he has told that errors might come, but not comparatively to metric cameras. But non-metric cameras, yes, we can make reduce as much as errors to be done, sir. Conclusion mainly I can give is industrial metrology. This vision system, which is there, is very useful, and since high model companies have started been using this because it reduces the basic disadvantages. It reduces manpower, but it increases lots of production. Loss of production will be there, but you need some time to increase the loss of product, decrease the loss of production, and there are possible of damaging of robot if it has not been maintained, if not been maintained properly. Sir, I'm done for the presentation, sir.